Amino acids, part 2. So in the last part we introduced kind of the general shape of an amino acid and the idea that they have these groups coming off of them. That they have 20 different possible things coming off that carbon. Well, let's talk a little bit about how we discuss them, we talk about them. Amino acids aren't found that often on their own. Like you can find an amino acid. This is our general amino acid structure. But the reality is this is not how you find them. Because, well, let's think about this for a minute. Let's say I have two of them near each other. Hydrogen. Well, what I have is I have an amine and I have a carboxylic acid. Think back to our reactivity. If I have a generic amine and I have a carboxylic acid, they react. What functional group do they make? Think about that for a second. An amine plus a carboxylic acid, the result is you get an amide. One of the hydrogens comes off, the OH comes off, you make some water, and you make an amide. So our amine and what used to be our carboxylic acid has linked together. Amino acids combine. So you will link them in series in order to make larger molecules because, well, while we can link these two, if I have a third, whatever our group, there's no reason those can't link. And then if you had another one, and so on, and so on, you can link those, and you could do this, well, for some amino acids, thousands of times. You can link amino acids together through a polyamide bond. All it means is that many amides. So you would take your first amino acid, you'd link it to your second one to make your first amide, then you'd take the end, you'd link it to your third to make your another amide, you'd take your fourth and link it on the end to make a fourth amide. You can just keep doing this. Because the molecule has both functional groups, it's able to hook on both ends to continue the chain. Way back, we talked about this. That's a polymer. Polymers were like plastics. This is a biopolymer. Life actually makes these long, continuously linked molecules in order to create all the different things that we construct our bodies out of, for the most part. Well, what does that end up looking like then? You get an H2, double bond oxygen, NH, double bond oxygen, NH, acid. And off each of these is some R group, whatever that R group or series of R groups might be. Well, you can link them together, and as you link them together, they become longer and longer and longer, and so they have slightly different names. Short chains are peptides. Think back to sugars when we had monosaccharides, disaccharides, polysaccharides, oligosaccharides. They have just different names for chain length. Short chains are peptides. Medium chains are polypeptides, and long chains are proteins. How many? Well, a long chain is usually greater than 50 amino acids, and short chains, that's not quite a great description, but generally they tend to be less than 10 amino acids. Like I said, it's not a perfect listing. The idea with proteins is that if you don't have enough pieces, you can't construct a large, complex molecule to do things with. think about it, if you link in Legos together. You can stick 3 or 4 Legos together, but they usually don't make a building or anything else. With proteins, they are the large structural elements as well as functional elements inside the body, and they need a certain size before they can do that. So they're really only proteins once they're up to a certain size. So we can link our amino acids together. Well, how do we do it? Generally, it's as shown above. We tend to go N-terminal, or N-terminus, the amine side, and we take that to the C-terminus, the carboxylic acid side. And so I always write, standard English, left to right. We start with the nitrogen on the left, we go over to the carboxylic acid on the right. And so by convention, this is how we draw them. You could have done it backwards, we chose to do it this way. This is the standard way. The terms change a little bit. So let's talk about some of the terms. So, when we had one lone free amino acid, so NH2, glycine, I'll put an R group. This is an amino acid. Like I said, we don't often find them on their own though. So it might be in a peptide or a polypeptide or a protein. But since the amino acid gets used to construct the protein or the peptide, when we go and look at this bit, we call this a residue. Technically at the moment, it's not an amino acid anymore. There's no more acid, there's an amide. But it came from the amino acid. So we tend to call something, let's just say we used serine, one of the amino acids. A serine amino acid is I can actually write that one then, is a hydrogen, and there's a CH2OH. So if we go up to this molecule and we kind of add that in, should draw it like that real quick. Sorry, dashes, boom. Well, that part of my polypeptide came from a serine. It is called a serine residue. The idea is it's not serine anymore. It's been reacted and connected to other things. But that component came from serine. It has the same R group as serine. If you look at serine over here, it's R group. Oops. I'll just rewrite that. Its R group is this CH2OH, and we still have the CH2OH. And so it is a serine residue when it is inside the peptide or the protein. Well, how do we then tell you what makes up the protein? It's made of a lot of different amino acids. Working from N to C, we will just write the name. So you could do something like valine, proline, lysine, etc., etc., etc. You could just connect a lot of them. That is not so hard when it's 3, but we said a protein had to be at least 50, and some of them can be thousands. This is not a viable means of showing larger proteins or larger peptides. So there's a couple shorthands for it. One is 3-letter shorthands. You can go val, pro, lys. So for each amino acid name, there's a 3-letter and there's even a 1-letter short version. Conveniently, there's 26 letters in the English alphabet, but only 20 amino acids, so there's 1 letter for each. Again, we're not learning the names, so we don't have to learn all the shorthands or the 1-letter systems for it. But just to show you kind of how it can be. Well, these just link together. So if you had a 3, it'd be here. If you had a 4, you might have a glycine, a tryptophan, an arginine, a phenylalanine, a histine, glutamate, methionine, serine, tyrosine, serine. You might have some molecule like this. In our case, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 13 amino acids long. This would be a small polypeptide. And again, this is a lot of writing. Generally, we use the one-letter codes if we're going to go through the order, just to simplify it quite a bit. Like I said, this class, though, we're not going to make you guys learn the 1 letters and the 3 letters, so while this is a educational description, we're going to move on a little bit from it. Because what I really want you to see with this, well, you notice there's a bunch of different ones. I've got a veil, a pro, a lysine, a glycine, a tryptophan, an arginine, a phenylalanine, a histine, a glutamine. I've got a bunch of different amino acids. Remember, there were those 20. And there are 2 that are duplicated, serine and serine over here. So what's going on? Why would I put them in this order? What does this represent? And what is this list do? This is actually an in existence polypeptide. It has a name. It is alpha melanocyte stimulating hormone. This was originally it was a suntan additive. They found that this series of amino acids together would activate your melanocytes, melanin. To produce more melanin, you'd get a darker tan. And so the idea was, if you're trying to tan and this was rubbed in, this series of amino acids is a signaling molecule, a hormone. We saw that for steroids. Some steroids were signal molecules that parts of your body responded to. Some, especially the shorter, the polypeptides, are signal molecules. They don't do anything on their own, they just click in like a key and turn on something else. So this would click into your melanocytes, activating them to produce more melanin. What they actually found with it, though, during testing was it also increased metabolism, it toned the skin, it ups people's sex drive. It was this miracle drug. So it actually got the name of the Barbie drug. As odd as that is, there's actually a second one we'll talk about in another video, probably. But it never quite reached market because it had a few other side effects. But just to give an idea of the wide variety of things that possibly can be interacted with.